Hello, Physics 20s. I want to spend some time on the last concept from chapter 8 anyway, on waves, and that's the Doppler effect. Uh, I'm confident a lot of you have heard of the Doppler effect. That's almost a pun because if you've ever been on the side of a road and you've heard a siren, an ambulance, or even just in a neighborhood, if you've heard an ambulance siren moving past you, you notice a definite decrease in pitch. Um, and even the sound of a car engine, you intuitively have heard it lots, but as it approaches, you hear kind of a higher pitch as it passes you. So I want to just quickly, the video I posted was excellent. The professor there did a fantastic job explaining the Doppler effect. I've got this animation up here just to run it quickly for you. Um, in this case here, if you can see, this red dot is radiating concentric circles of sound waves. And I've got this little microphone here. If we bring it close enough, I don't know if you can hear that, but it's registering 2 waves per second, which is the which is the same as the source frequency. Okay, so the source is kind of radiating waves 2 times per second, and we're detecting them at 2 times per second. Now that's not very surprising, but that's just because the object isn't moving. So if we move the microphone away and then we actually send this towards the microphone at, we'll maybe go like 0.76 the speed of sound, then you start to see the Doppler effect. See, the waves are still being produced at 2 times per second, but because the source is moving, the waves in front of it are bunching up, and when it hits the microphone, you kind of hear them all at once, but then after it passes, you hear them at a lower frequency than 2 times per second. It's 1.14 or whatever, okay? And as you can imagine, and some of you have already studied this too, as we go faster, as you approach the speed of sound, that would be Mach 1, okay? So here you're traveling just as fast as the waves of sound that you're producing. And so they bunch up in front of you as this cone. Well, it's actually not a cone yet, but it's just a big wave front. And yeah, okay, there's our microphone, picking them all up at once. This is not uncommon in terms of if you see a jet up in the summer sky at high altitude, you'll see it way before you hear it. In fact, the jet almost passes over your head, and then it's a little bit past you, and then you start to hear the rumblings. Now, if the jet was going supersonic, that's faster than the speed of sound, it now leads its sound waves, and it forms this really cool cone, okay? So it's like a sonic cone. And when all of that sound, like for an observer, you definitely wouldn't hear anything until it's past you. But if you were down here, I'm just moving my microphone, you could see it go past you. And then all of those waves, well, the microphone barely caught that one, but all those waves would show up all at once in terms of that leading cone. And that's what a sonic boom is. Okay. And there's regulations against aircraft flying supersonic at low altitude because it's just really disruptive. Apparently, if it's potent enough, you could maybe, do some damage to windows and stuff like that. But that's basically the Doppler effect. So what I want you to know about the Doppler effect is tied in the notes here. So I'm just going to go through these. Christian Doppler was the Austrian physicist who studied this effect, and famously I think it was either a trumpet player or a musician. I want to say it was a trumpet player, but I don't know for sure. He had a musician play an instrument on the flat deck of a rail car, and Christian Doppler just sat at, say, the train station, and this musician would just play a single note as he approached the train station. And Christian Doppler noted a higher pitch as he was approaching and a lower pitch when he passed, and started to do the math to explain that phenomenon. I know the video did a great job of talking about light. We study light in Physics 30. Light waves follow the same phenomenon as sound waves because they're waves. And if a star is moving, if it's moving towards you, we have a blue shift in the waves because they actually shift to higher frequencies or shorter wavelengths. And with light, as the video did a great job explaining, with light, shorter wavelengths means a bluer color. Longer wavelengths means a redder color or a shift towards red. So this is the evidence actually that the universe is expanding, which is really cool, because when we look at stars, they're almost all moving away from us. In fact, everything in the universe is mostly moving away from us. So that's a cool example of the Doppler effect. Here, this is just another diagram showing the position of the source at A, B, C, and D, and the waves will emanate from that source, but you can see towards the right, the wavelengths start to get bunched up. Just for matter of reference, you'll see this in just a second. These wavelengths, we tend to call these wavelength number 1, and I like to think of them as the leading wavelengths, okay? The wavelengths that are bunching up. The ones behind, like, sorry, I guess that should be perpendicular, but anyway. So this wavelength, we call it wavelength number 2, and I like to call those the trailing wavelengths, okay, in this phenomenon. What's really cool about the Doppler effect is the velocity. We sometimes call it VW. This is the velocity of the wave. And for a Doppler effect, the velocity of the wave stays constant. Okay? Just because you're moving doesn't mean the sound you're producing is going to move faster or slower. Sound is kind of a fixed speed. Yes, it's based on the density of air and the temperature and stuff like that. But the velocity of the wave stays the same. So this is different than if you remember back to refraction, where we had the ripple tank, and I was telling you that the frequency stays the same, like the number of waves generated per second stays the same. Well, in this case, the frequency basically to the observer, the frequency doesn't stay the same. It's the velocity this time. Okay, so that means if the velocity stays the same, if you look at the equation, okay, so if this variable doesn't change, then these two have to change. So if the wavelength goes down, then the frequency has to go up, and vice versa. Okay, so when the wavelength gets bigger, that means the frequency has to go down. So it's kind of a cool parallel, but if you can follow that mathematically, that's exactly what's going on. The formula, the Doppler effect formula on your formula sheet is this right here, okay, but there's the two variations if you're starting to see it. FD stands for Doppler, the Doppler frequency, and I like to think of this as what you hear in your ear, okay? So this is the observer's frequency that the observer hears. Oh, sorry, wait, I'm thinking of two things here. So what you hear in your ear, okay? And the other components hopefully kind of are a little more straightforward. VW, I've already identified that. That's the velocity of the wave. So that would be like the speed of sound. Or if it's a water wave, it'd be the speed of the water wave. And the VS is the speed of the source, or velocity of source, I guess. But typically we're just dealing with speeds here. The speed of the source. And Fs is the frequency of the source, or sometimes we call that the true frequency. Okay, so that would be, whatever the frequency of the sound is from the source, just stationary, right? Like, obviously, if a police car is, think of it as a police car siren if the police car is not moving. So you hear that, that would be the true frequency. What's really interesting about this mathematically, to me, is if the object isn't moving, okay? So look at this formula. If Vs is equal to 0, then there's no change in the denominator. It's just going to be VW over VW, whatever that happens to be. And that would just be 1. So that would mean then that what you hear in your ear is exactly what the true source frequency is. So the only variation, and Christian Doppler figured this out pretty quick, is that The only variation is if the source is moving. Now, technically, the observer could also be moving. We're not going to make it that complicated for you. You know, like if you're running towards a police car that's driving towards you, then the math gets amplified a bit because both of you are moving, but we're not going to go that far. So we're basically just going to keep the observer stationary, and we're going to just let the source move. Okay. So anyway, I guess, sorry, I kind of double labeled that, I guess. Sorry, I just was trying to explain that a bit better for you. If the source is moving towards you, you'll notice in the original formula, there's a plus minus down here. Okay, so you see that there, that plus minus around between VW and VS. So all you have to catch in using this expression, it's not too difficult, but if you miss it, then you'll get the opposite answer. If it's moving towards you, then you subtract VW minus VS. But if it's moving away from you, if the source is moving away from you, then you add. And yes, the pitch gets lower and higher respectively. Okay, so maybe I want to just do question number 2 with you. I'll post the answers here, and then I'll make another. I'll do one other one with you. Okay, so trains traveling at a speed of 30 meters per second. If you can identify that right away, that would be the speed of the source. With these questions, just go really slow because there's a lot of variables, and if you just take your time to identify what everything is. Okay, its whistle, sorry, that's a typo. Its whistle generates a sound wave with a frequency of 224 hertz. That would be the source frequency. That's what's being generated. That's what the train whistle would sound like to an observer if neither one of you were moving. Okay, but you're standing beside the tracks as the train passes you with the whistle blowing. What change in frequency do you detect? What change in frequency do you detect? So that's like delta F. You detect for the pitch of the whistle as it passes if the speed of sound in air is 330 meters per second. So there is VW. Okay, so what we have to do in this case is there's going to be 2 Doppler frequencies, right? You're going to hear a higher pitch when the train is approaching you, and then you're going to hear a lower pitch when the train has passed you. You need to find both of those frequencies and then get the difference between the two. Now, it's not too bad, but you definitely have to do it twice. So in this case, we would look at VW over VW, the first one, and I'm going to subtract VS for the first calculation, okay? Because it's approaching me, and I put a little shortcut here on that. If it helps you, if an object's moving towards you, my brain kind of thinks, well, the distance between us is decreasing, so I should subtract in the denominator. I don't know if that helps you, but yeah, so if an object is approaching you, so you subtract. If it's moving away from you, then you add in the denominator, okay? So so yeah, we'd plug in 330. Sorry, I'm just going to write over the next question. Sorry. 330 again would be in the bottom. And then I'd subtract from that the speed of the train, which is 30 meters per second. Okay. Times the source frequency, which is 224. Okay, so really you can kind of get a sense here. We're getting a percentage of the true frequency, either below the true frequency or above it. And in this case, yeah, it's going to be below. It's going to be above. Sorry, we're going to get a higher frequency here, and we do. So when you have to do all of this first and then times it by 224. We're going to be multiplying it by something greater than 1, and we get 246.4 hertz. Okay. Now, if I do the other one, I won't write it all, but you get the idea. Here we would have to add VS. Okay, so effectively I'm making the denominator bigger than the numerator, if you can follow that. Okay, so that my final Doppler frequency will be lower. Okay, and anyway, I guess my point is, like, practically when you do these, you should expect the numbers to be higher or lower depending on is the source moving towards you or is it moving away from you. So yes, in this second one, I think I got 205.3, okay, hertz. Okay, so this is the high frequency coming in, and here's the low frequency after it passes. So the change in frequency is just going to be the difference between the two. You just go 246 minus 205, and I get a change in frequency of 41.1 hertz. That is what the observer would hear in terms of a change in their frequency. Okay, so again, if I did that too fast, you can slow that down. I think you guys can get this well enough though. So here's a little, just that reminder I was alluding to before. You add if the source is moving away from you. That means if in an objective sense, the distance between you is increasing. I know the speed isn't though, so sorry if that's a little confusing tip, but yeah, you subtract if it's moving towards you. Now, this we emphasized already. When considering the Doppler effect, the velocity of the wave doesn't change. The speed of the wave is fixed. Okay, VW, that doesn't change. What does change is the Doppler frequency for the observer, what the observer hears in their ear, and also the wavelength, okay, depending on who's moving. But obviously in our cases, it's just the source that's going to move. Now, these are two extra formulas that are not on your sheet that I encourage you to add to your sheet while you're doing review, and you can definitely use it on the tests too. And I want to show you where I got these from, okay? Because you'll notice in the Doppler effect formula, wavelength is not in there. There's no wavelengths directly in this formula. But sometimes you are given a wavelength, like you're given the wavelength of the leading wavelength or the trailing wavelength. And then how can we use those? Well, let me show you just briefly for one of these, okay? Again, you can just use the formula, but I want you to see I didn't just make this up, okay? So the Doppler frequency is equal to VW over VW plus or minus VS times the source frequency. There's no wavelengths in here. What we can do though is I can, for the Doppler frequency, that I can express that as VW is equal to the Doppler frequency times whatever wavelength I'm dealing with. And for leading wavelengths, remember our convention, for leading wavelengths, I'll just show you that fast. We are going to use wavelength number 1. We're going to call that the leading wavelength and wavelength 2 the trailing wavelength, okay, just for consistency. So what I can do is, and again, this is the fixed, the speed of the wave is fixed. That can't change. So these two can change. The Doppler frequency and the wavelength can change. And if I'm dealing with this Doppler frequency, there it is there. Those are the same. So if I just divide by wavelength 1, I now have a new expression that I can tuck in to the Doppler frequency. So I'm just going to do this to the right. This might get a little messy here, but I can go VW over wavelength 1 is equal to VW over VW. Now, again, for leading wavelengths, I have to subtract, okay, because it's approaching me, right, times the source frequency. Now, so this looks really messy, and there's a whole bunch of VWs, by the way. So we can simplify this expression, and I want you to see that because VW is on both sides in the numerator, I can divide both sides by VW, and that cancels both of those VWs. So then in an intermediate step, I have 1 over wavelength 1 is equal to 1 over VW minus VS times FS, okay? Now, again, I don't like fractions in the denominator. They confuse me a lot of times. So if I multiply the left-hand side by wavelength 1 and do that to the right-hand side, and if I multiply the right-hand side by VW minus VS, effectively the denominators trade sides and they come up, okay, if you can follow that. So I have Fs times wavelength number 1, okay? And then very simply here, just because kind of the convention is to use the speed of the wave, I just add Vs to both sides, and I have a new expression, plus V1, okay? Now this is for leading wavelengths, and that's exactly what this is right here, okay? So this formula that we just derived is that one. Okay, so I'll pull that back up. All right, and if we do the same thought process, but we do it for trailing wavelengths, we get this expression here. Okay, so both of those can be really useful, and I'll just show you quick how we can use one of them, and then I'll let you guys practice some of these. Okay, so in this practice question here, this is a ripple tank, so we're dealing with water waves, and again, just go really slowly. It looks like it's moving to the right, like you can tell the waves are bunched up here on the right, and the waves are stretched out on the left. So, I mean, this object's clearly moving to the right. The wave source in the ripple tank's moving to the right. The source has a true frequency of 2.75 hertz. So that would be Fs, the source frequency, okay, the true frequency. The wavelengths of the waves that are moving to the right, sorry, this should be wavelength 1 ahead of the source. They're 1.1 centimeters, or 1.17, sorry, centimeters, okay? And the wave source is traveling at a speed of 4.36 meters per second, centimeters per second, sorry. That is Vs. And then it says, what is the speed of the waves? VW. Okay, so I have the source frequency, I have wavelength number 1, I have the speed of the source, and I'm trying to find VW. Okay, now you could do this in 2 steps, but what I'm trying to help you see is we've already derived a formula that we can work with to manipulate an equation and solve for things. In fact, I've already got it. Okay, if I've got the leading wavelength, and I can use that to find the speed of the waves. So I can just go VW is equal to Fs times wavelength 1 plus Vs. Okay, now this one, I know it's a little confusing because on this one we're adding Vs in this case. Whereas in the one you were learning initially, you subtract if the source is moving towards you. Okay, so I apologize for the complexity there. I hope that's, but if you just lean on your formula sheet because you know the relationships, I think you'll have no problem actually doing this math. Okay, and if we actually did that, so we plug in Fs as 2.75. By the way, the wavelength is in centimeters. You can leave it in centimeters, and you can leave the source velocity, or yeah, the speed of the source in centimeters, because look at your answers are all in centimeters per second. Okay, so there's no need to change it to meters. Just so if you catch that, I know I've been hammering changing to meters all the time. This is an exception. So, but yeah, if you do that math, you should get a, all right, sorry, let me double check here. Yeah, 7.58 centimeters per second would be the speed of the waves in the ripple tank. Okay, so anyway, I hope that's helpful. There's so many cool demonstrations about the Doppler effect. And if we had some time, we could maybe do some more of those. But for now, that's the explanation for the math, and I will let you try those over the next day or so, and I'll also post the answers. So anyway, keep up the good work, you guys.